we'll go with the problem. So far we have discussed the formulas, and that formulas we'll be using in the classes. Okay, so this is our first problem. So you have a continuous beam, one is hinged, other three are roller supports. Okay, so whereas analyze the continuous beam by flexibility matrix method, and EA of the beam are constant throughout. So first thing in the analysis method is you need to consider the degree of redundancy, okay, or degree of static indeterminacy. For that we will take the formula R minus 3, that is number of redundants minus 3 are the equilibrium equations, that is redundants are here are 2, one is horizontal and next is vertical. Okay, here the moment is free about hinge support A, and whereas for joint B you have one force that is acting vertical, at C it is one force, and at D is one force. So totally we have 2, 3, 4 and 5. So 5 minus 3 it is 2. So here the degree of redundancy is 2, so the two coordinates we are supposed to release. Okay, please remember, and I have said you in the previous class with respect to the previous problem also and in introduction. Now also just listen, we are supposed to remove those two redundants. As you can see, here you have 2, here you have 1, 1 and 1. With respect to support A, you have 2 redundants. With respect to support B, you have 1, C 1 and D 1. So here if you want to make the structure as determinate, that is degree of redundancy should become 0, then you should release 2 redundants. Okay, forces. So what are those 2 redundant released forces are? One you can release at B and one you can release at A. But what happens is the structure, this becomes roller condition and this becomes just a joint. Okay, here what happens is the structure becomes totally roller condition and it is unstable. So we should see that the structure is stable as well as determinate. So in this condition, if you remove the C and D, so what happens, one support is released from C and other support is also released from C. So what happens, the portion from B to D becomes a cantilever portion, hence the movements with respect to the loads and movements released due to this member also becomes difficult. Okay, so this is also a complicated process. So the best process is, we cannot release 2 over here, that is hinges A, one is horizontal and vertical, because if you release this total hinge, then the whole frame becomes roller as well, and this portion becomes a cantilever. Again the problem comes with instability. So the best position is remove supports at B and C. Okay, so the best process is, we can remove the support, one force at B and one force at support C. So what happens is these two becomes joints, and hence the structure will be stable at one end with hinged, one end with roller. Okay, so we will apply 2 forces over here. One is moment about B and moment about C. Okay, when we release these forces, so this form matrix is, we form a matrix of 2 by 2 by removing the supports at B and C. The movements at C are taken as redundant forces. So displacements due to the given loading in the release structure are calculated by conjugate beam method. So as you have released these frames, before we go for that, we are supposed to analyze the bending moment. Okay, in this, as you know, the second step that we are doing it here, analyze the bending moment using the formula. As you know, the formulas are, for UDL load it is WL square by 8, for point loads at center it is WL by 4, WL by 4. So now the moments are 60 kilonewtons, 150 and 100 kilonewton meter moments. So to form this as conjugate beam concept, that is this bending moment diagram, so bending moment values we'll consider in terms of loads. Okay, we are converting in the conjugate beam in terms of loads. For that we'll take the maximum ordinate loads at each point. It is M by A, 60 by A, BC is 150 by A, and CD is 100 by A. Okay. Next, after that, forming the delta matrix. Just in the previous class, you have seen the formation of delta matrix with respect to flexibility when we are defining differences between matrices. Okay, so this is the delta matrix. Okay, delta L, where delta 1 and delta 2L should be calculated. So delta 1 is the loading with respect to this loading condition at point B and at point C. So delta 1L is due to these two and delta 2L is with respect to these two. Okay, so delta 1L is, as it is a parabolic, so delta 1L represents with respect to B, not A. So B, it is considered 1 by 2 of 2 by 3rd of center of gravity into 60 by A into 4. 4 is the span distance. Okay, so CG acts at the 2 by 3rd of the distance, so that is why for the parabolic conditioners parabolic arc, so that is why we have taken as 2 by 3rd plus this 60 by EA is the vertical distance, okay, for the arch, and 4 is the horizontal distance. Okay, that is we are taking the area of the section. Okay, so next 1 by 2 into 150 by A into half into 4, that is, as the next portion is of triangle, we will take half of the area, half of L into B, whereas the length of the condition is 4 by 2. Okay, and whereas height is 150 by A. Okay, so that is 80 by A plus 150 by A, it is 230 by A, whereas 2 gets 4 cancels out, 2 cancels out, 4 by 3. Okay, 2 ones are 220s. Okay, 80 plus 150 by A. Next, if you go for delta 2 matrix, that is 1 by 2 into 1 by 2 of 150 by A into 4 plus 1 by 2 into 1 by 2 into 100 by A to 4. So 1 by 2 into 1 by 2 into 100 by A into 4, that is 150 by A plus 100 by A, which is 250 by A. Now we have formed the delta matrix. Here we don't have any sinkings or sway conditions to consider or lateral loads, so the delta matrix will be zeros and zeros. Okay, you have delta is minus delta L matrix, where delta L is 0 zeros and delta matrix is 0. Delta LLs are delta 1L and delta 2Ls. Next, going for the flexibility matrix. So as we have released forces at B and C, first case we will apply unit load at B at the first coordinate, and next, as we have seen in the differences, we should apply the coordinates. So this is the first coordinate, and at C you have the second coordinate. So with respect to first coordinate, see the delta values you will form here as delta 11 and delta 21. So clearly remember delta 11, 1 is the displacement which is taken, okay, with respect to the first coordinate. Okay, and next delta 21 is the first displacement with respect to the second coordinate, okay, due to the first displacement at second coordinate. So delta 11 is the first displacement with respect to first coordinate, that is you are applying 1 kN of load. Due to that you form a triangular section. Okay, that is the load condition is 1 by A. Similarly, as you have done here, the same way you will do it here considering the conjugate beam, that is 2 by 3 into 1 by 2 into 4 into 1 by A plus 2 by 3 into 1 by 2 into 4 by A.